So radical addition of hydrobromide is our next topic. So in chapter 8, actually section 8.5 is where we first encountered hydrohalogenation of an alkene. And under conditions without peroxides present, we saw that we had the bromine adding at the more substituted carbon position and the hydrogen at the less substituted position. And that was termed Markovnikov's addition. In the presence of peroxides, we also saw that we had anti-Markovnikov's addition, with the hydrogen being added to the most substituted carbon and bromine at the lesser substituted. So peroxides initiate the radical mechanism for addition of HBr across the alkene bond. So when we left off, we were referring back to chapter 8, maybe section 8.5, and that was the regioselectivity in a Markovnikov addition. In the ionic addition mechanism, we have bromine adding to the most substituted carbon. And in chapter 8, there was some discussion about the effort to sort out the regioselectivity because of the presence of peroxides led to the anti-Markovnikov addition, and that peroxides initiate a radical mechanism. So in the ionic mechanism, bromine adds to the most substituted carbon, and in the ionic mechanism, we have the anti-Markovnikov addition. So we begin with initiating thermal hydrolysis of a peroxide to initiate the formation of a bromine radical from HBr. So we have our homolytic cleavage of the peroxide, that peroxide going on to abstract a proton from HBr to give us a bromine radical, which subsequently approaches the alkene and adds to the double bond in such a way to produce the most stable free radical intermediate, and that is the tertiary radical. So addition on the less substituted carbon, the anti-Markovnikov addition product, results in the more stable free radical, tertiary free radical. As you can see, addition on the other end of the bond leads to the less stable secondary radical. So this is the explanation for the anti-Markovnikov addition through the free radical mechanism. So we see this more stable tertiary free radical formed, and then the carbon radical is able to abstract a proton from HBr to form our addition product and regenerate the bromine radical in this propagation step. And then just to round this out, most of the radicals in solution at any given time will be bromine radicals. So their combination is going to be the typical termination step for coupling of two bromine radicals to form bromine. But the combination of any two radicals would be termination. So looking at the thermodynamics of the anti-Markovnikov addition reaction, this is generally spontaneous, thermodynamically favored. Radical addition of HCl and hydrogen iodide are not spontaneous. The reactants are favored in that case. So we're going to look at the enthalpy and entropy terms in this reaction to understand the thermodynamics of each of these halogen reactions. So we're going to look at the two propagation steps one at a time. So let's consider the halogen radical adding to the alkene. We have two species combining to form one species. So the level of order is increasing. So there is a decrease in entropy. So our entropy term is going to be positive, regardless of the identity of the halogen. So there's going to be no entropic contribution to this reaction being spontaneous. We're going to need to have an enthalpic favorability that's large enough to offset the positive entropy term. So in the case of HCl, we have a net release of energy. We have a negative delta H. For HBr, we have a negative delta H. For hydrogen iodide, it's endothermic. And this is because the iodide radical is more stable than a carbon radical. So its addition is not favored. That adding the iodine radical to generate the carbon radical requires energy. So that's not thermodynamically favored. Both terms are positive, so delta G will be positive in all cases. Looking at the second step, regenerating the radical, again, beginning with the entropy term, we have two species, hydrogen abstraction. We have two species and there's a hydrogen abstraction. So we begin with two species, we end with two species. The level of disorder has not changed appreciably. So the entropy term is essentially zero. So that doesn't factor into our overall favorability. Looking at the enthalpy term, for HCl, for that bond to break, it requires an input of energy. That bond does not want to break. HCl is it's thermodynamically favored to stay as HCl, and that's due to the instability of the chlorine radical. HBr, abstracting the proton from HBr, is enthalpically favored. We have a net release of energy, and with HI we have a net release of energy. Given that the entropy term is zero, it's going to be very difficult to find a temperature that would allow this term to offset the positive enthalpy for the abstracting the hydrogen from chlorine. So we won't see an anti-Markovnikov's addition with HCl. With HBr, we will. And with HI, even though this step has a negative delta H, the first step cannot proceed. So this step really is irrelevant because it just doesn't occur. So only HBr will participate in the anti-Markovnikov addition or the radical addition of bromine across the double bond. Now, a reminder about stereochemistry. When we have addition reactions, we often form a new chiral center. So if the substrate wasn't chiral, then we're going to have a racemic mixture from that new chiral center. If our alkene contained a stereocenter, then we're going to obtain a mixture of diastereomers from that addition.